In the vast theater of nature, a constant struggle for survival unfolds, driving species to evolve and adapt in response to each other's advancements. This phenomenon, known as coevolution or more dramatically as evolutionary arms races, showcases the intricate dance of predator and prey, parasite and host, each pushing the other to new heights of evolutionary innovation. From the fastest land animals to the stealthiest parasites, these arms races have shaped the natural world in fascinating ways, even influencing human biology and psychology. The pronghorn's mysterious speed. One of the most intriguing examples of an evolutionary arms race involves the North American pronghorn, the second fastest land mammal on Earth. For years, scientists were puzzled by the pronghorn's ability to reach speeds of up to 96 kilometers per hour, far outpacing any of its current predators in North America. The mystery deepened when considering that even the cheetah, the only land animal faster than the pronghorn, had never shared its habitat. The answer to this riddle emerged in the 1970s with the discovery of fossilized remains of a North American cheetah-like cat. This extinct predator, closely related to the modern African cheetah, was believed to have preyed significantly on pronghorns. Scientific studies analyzing carbon and nitrogen isotopes in the fossils suggested that pronghorns may have constituted a substantial part of this ancient cat's diet. This revelation paints a vivid picture of an evolutionary arms race that played out over millions of years. As the North American cheetah evolved to become faster, the pronghorn responded by developing even greater speed to evade capture. The result of this long-standing competition is the incredibly swift pronghorn we see today, a living relic of an ancient battle for survival. Interestingly, while the pronghorn may have lost many individual encounters with its speedy predator, it ultimately won the Evolutionary War. The extinction of the North American cheetah left the pronghorn with abilities far beyond what its current environment demands, a testament to the lasting impact of evolutionary pressures long since vanished. Bats versus moths, a battle in the night sky. Another fascinating evolutionary arms race plays out in the darkness of the night sky between bats and moths. Many bat species rely heavily on insects for food, using sophisticated echolocation to locate their prey mid-flight. This presented a significant challenge for moths, who found themselves on the menu for these skilled nocturnal hunters. In response to this threat, tiger moths evolved an ingenious defense mechanism, the ability to produce ultrasonic clicks, similar to those used by bats for echolocation. These clicks serve to confuse the bats, effectively jamming their sonar and allowing the moths to evade capture. Studies have shown a marked decrease in successful catches when moths employ this clicking strategy. However, bats didn't simply concede defeat. They counter-evolved by adjusting the final phase of their echolocation, known as the terminal buzz phase. By lengthening this phase, bats can more accurately pinpoint their prey, even when faced with the moth's sonic interference. This ongoing back-and-forth showcases the dynamic nature of evolutionary arms races, with each side continually adapting to the other's latest defense or attack strategy. The cuckoo's deception, parasitism, and egg mimicry. Perhaps one of the most subtle yet fascinating examples of an evolutionary arms race occurs between the common cuckoo and its host birds. The cuckoo is a brood parasite, laying its eggs in the nests of other bird species and tricking them into raising the cuckoo chicks as their own. This strategy often results in the demise of the host's own offspring, as the cuckoo chicks outcompete them for resources. To combat this parasitism, host birds have evolved the ability to recognize and reject foreign eggs in their nests. In response, cuckoos have developed an extraordinary ability to mimic the eggs of their hosts, producing eggs that closely match in color and pattern to avoid detection. A study comparing cuckoo parasitism in Hungary and Japan provides insight into the progression of this evolutionary arms race. In Hungary, where the relationship between cuckoos and their warbler hosts is believed to be older, cuckoo eggs more closely match those of the host. In Japan, where the relationship may be more recent, the match is less perfect. Interestingly, despite the difference in egg matching, rejection rates by hosts are similar in both locations, suggesting that the evolution of egg mimicry and egg recognition may not occur at the same pace. This ongoing battle of deception and detection highlights the intricate coevolutionary processes at work in nature, with each party constantly adapting to the other's latest strategy. Snakes and primates, a neurological arms race. Our final example brings the concept of evolutionary arms races closer to home, involving the long-standing conflict between venomous snakes and primates, including humans. The snake detection hypothesis proposes that primates have evolved a heightened ability to quickly identify snakes due to the mortal threat they pose throughout our evolutionary history. Studies support this hypothesis, showing that humans can identify snakes in blurry images faster than other animals. This suggests that our brains have been evolutionarily primed to rapidly process and react to snake-like stimuli, a trait that would have provided a significant survival advantage to our ancestors. In response to this increased detection ability in primates, venomous snakes like cobras have evolved their own set of defensive adaptations. These include warning colorations and displays such as hooding, which serve to quickly identify them as dangerous to potential threats. Some species have even developed the ability to spit venom, allowing them to defend themselves against primates who might use tools or projectiles to attack from a distance. The evolutionary arms race between snakes and primates has not been one-sided, however. Primates that regularly encounter large, neurotoxin-producing snakes have developed increased resistance to these toxins compared to primates that don't face such threats. This biochemical adaptation showcases how evolutionary arms races can occur not just at the behavioral or morphological level, but at the physiological level as well. Conclusion: the never-ending race. These examples of evolutionary arms races demonstrate the incredible dynamism of natural selection. From the lightning-fast pronghorn to the deceptive cuckoo, from the sonic battles of bats and moths to the neurological arms race between snakes and primates, we see how the constant pressure to survive and reproduce drives species to remarkable adaptations. These arms races have profound implications for our understanding of evolution and ecology. They highlight the interconnectedness of species within ecosystems and demonstrate how the fate of one species can be intimately tied to that of another. They also reveal the power of selective pressures in shaping the traits of organisms over time, sometimes resulting in capabilities that seem excessive in the current environment, as with the pronghorn's speed. Moreover, these evolutionary contests underscore the ongoing nature of evolution. They remind us that the natural world is not static, but in a constant state of change and adaptation. As environments shift and species interact, new pressures arise, driving further evolution. For scientists, these evolutionary arms races provide fascinating avenues for research. By studying these interactions, we gain insights into the processes of natural selection, the development of complex traits, and the dynamics of predator-prey or host-parasite relationships. Furthermore, understanding these evolutionary processes can have practical applications in fields such as pest control, conservation biology, and even medicine. As we continue to explore and understand these evolutionary arms races, we're reminded of the incredible complexity and beauty of the natural world. Each species, with its unique adaptations and strategies, tells a story of millions of years of evolutionary history. And as we've seen, sometimes these stories are intimately intertwined with our own, shaping not just the world around us, but our very perceptions and instincts. The next time you marvel at a pronghorn's speed, hear a bat's ultrasonic call, or feel an instinctive fear at the sight of a snake, remember, you're witnessing the results of nature's grand, ongoing experiment in survival and adaptation. The evolutionary arms race continues, and only time will tell what remarkable adaptations the future holds.